Thank you very much. Very nice that I can join you here, even if we are 700 or 1,000 miles apart. I will talk about fertilization and kind of a summary of all fertilization trials that we have conducted in Sweden the past 60 years, and I will end this presentation how fertilization could mitigate climate change. So I will try to explain every graphs because you will have some figures here, and I try to be kind of pedagogical here. But for our boreal ecosystem and also cold temperate ecosystem, usually nitrogen is the main limiting nutrient, because if you fertilize with phosphorus or potassium or kind of other nutrient, you will have no fertilization response in most cases, but not always, but in most cases. So if you have nitrogen and you add other nutrients combined with nitrogen, you will have very small effect of the other nutrients, but nitrogen in itself has a very strong effect on growth, especially for conifers in our country. But I guess that urban, you got an overview that the most common tree species in Sweden is Norway spruce and Scots pine. And then we have 10% deciduous trees in Sweden. So we have not as many tree species as you have in Canada, for example. Just to start with why fertilization increased growth, there's mainly three different reasons. I think the main reason is that the increased production. I mean, fertilization increased production of foliage, and that means increased photosynthesis, and that in the end leads to increased growth and stem growth. You see this aerial photo on the left-hand side here. You see the dark green patches there. It's fertilized square plots there. It's 50 times 50 meters, but you see like maybe 20 different square plots altogether, and then you have control plots in between. It's not that marked, but it's quite drastically, and that's because that you have more foliage, but also that you have a shift in color as well. You can maybe, in some cases, if you fertilize young stands, you can increase foliage biomass by 200–300% compared with unfertilized unfertilized plots. Another thing is that it's fertilization change partitioning of photosynthetic products, and it's like if you fertilize, you have a lot of nutrients in the soil, or at least you have considerably more nutrients in the soil. And then we have seen that the production of especially fine roots is in relative terms much less for unfertilized areas compared to fertilized areas. And that means that more in relative terms is allocated to, for example, stem growth. So more is allocated to above ground parts of the tree. And the third thing is that you will get the more effective photosynthesis. Usually when we measure nitrogen concentration and we measure photosynthesis, we have higher photosynthesis when you have higher nitrogen concentration in needles. And it can be like 20% higher. So it's more effective. That will also, but the main reason is the increased amount of foliage. And then I think the partitioning is the second reason, and the last reason, the minor reason, is photosynthetic efficiency. So this is a graph you know when you have a rotation forestry. You see this solid black line where it says current annual increment. It peaks usually at the time at first thinning, but it takes some time for it to reach, for the stand to close. And it takes longer, for example, for Norway spruce to build up the maximum amount of foliage. you see the other curve is kind of the, let's say, the potential uptake of nutrients. That you see that in the second half of the rotation period, you have a lower uptake of nutrients. And it's usually during this kind of part of the rotation period where you have operational fertilization in Sweden. And it is mainly by economical reason, because if you invest in the fertilization, you will have kind of the income as soon as possible. So it's kind of a, you know, this is the kind of how you calculate economy usually in forestry. But the potential uptake is actually larger in young forests when they build up the foliage. So what you can do is that you can increase the production quite drastically if you fertilize in young stands, and especially in Norway spruce stands, where you can build up a lot of foliage. And it's important also to know that the concentration of nutrients is at least 10 times higher in foliage compared to other parts of the tree. For example, if you compare with the stem or branches, the concentration of nutrients is much, much higher in needles. And what happens if you fertilize a young stand is this time before, from the planting to the stand closes, will decrease quite drastically if you fertilize in young stands. But fertilization in young stands is not practiced in forestry today in Sweden. It's only during the second half of the rotation period. Just some basic information about it. It's most common that you do it 10 years before clear cut, and it's because that you will have the income just 10 years after you have this cost for the fertilization. And usually it's quite good economy. It have an interest rate of like 10% of the capital or the cost. A normal supply in Sweden is 150 kilos of nitrogen per hectare. You usually use a fertilizer called Scots in Sweden, and it contains 27% nitrogen, and then it contains also some calcium and magnesium, and usually some boron as well. And why you have calcium and magnesium is that you have a bedrock material when you produce a fertilizer, so that this will come along, and it has also a positive effect on pH as well, that it will not kind of the pH will not decrease when you use this fertilizer. And if you fertilize repeatedly, you can see on very poor soils that you can have boron deficiency, and that's why you have boron in these kind of fertilizer. Repeated fertilization occurs occasionally, but it's not very common. Usually you fertilize only once in Sweden. Now I would say it's mainly spread by helicopter. 70% of the area, or the fertilized area in Sweden, is made by helicopter, and well, like 30% by tractor. What you can say about that is the amount of fertilized land has changed quite a lot during the past 60 years. In the beginning it was low, but then in the 70s and the end of 70s and beginning of 80s, we have like 200,000 hectares per year that were fertilized in Sweden. I think now we are down at like 50 to 60,000 hectares per year. It's not very common in Finland, but it has been more and more common in Norway, actually, that they have subsidies from the Norwegian state. By at least half of the fertilization is paid by the state, because they want to mitigate climate change by fertilization. So I think they've gone from 0 hectare to 30,000 hectares in 3 years. So that's quite drastic increase, actually. What happens when you fertilize with nutrients? You have a nitrogen leakage, usually something between 2 to 10 kilos of nitrogen per hectare if you fertilize with 150 kilos of nitrogen. So it's like 6-7% of the nitrogen can be leached out. This is below the rooting zone. Then I said that by economical reason, fertilization is most common 10 to 15 years before clear cut. Some figures, the kind of the extra growth you achieve when you fertilize is like 10 to 17 cubic meter per hectare in central Sweden, and in northern Sweden you have usually a little bit higher increase in production, so it's like 16 to 21 cubic meter per hectare. And the fertilization effect lasts for 7 to 10 years. Usually it's a little bit longer for Norway spruce, and that's because of the longevity of needles slightly compared to Scots pine that have lower longevity. To some extent, especially when it comes to Scots pine, is that you can have an extra increase in that you get more paid for the logs, especially the 2 first logs for when you fertilize, because they will have higher dimensions, and some of these high dimensions is better paid. So you have more paid if per unit volume, if you say so. And the fertilizer constitutes usually, it depends of course on the market and the global market, but 2/3 of the total cost comes from the fertilizer costs, while transport of fertilizer equipment and the spreading of fertilizer is like 30% of the total cost. So that's, and usually today it costs like 3,500 Swedish crowns per hectare, and what that means in dollars per acre I'm not sure, but I think Brian can help us with that if you calculate. But it's with that kind of fertilizer cost, it's quite a good economy when you fertilize. So what kind of soils do we use when we fertilize? When it comes to silviculture, we should not thin the stand or clear cut the stand within 8 years from the fertilization. So we have to kind of keep the stand untouched, otherwise you will kind of thin out the fertilization effect to some extent. Yes, and I've said that usually after first thinning, that when you have a FGrOW system, and in older stands it's the most common time when you fertilize. And we try to avoid stands with large patches, because these are unproductive kind of areas that we want to be as effective as possible when we fertilize. If you're going to use a tractor, you need a FGrOW system, but if you use helicopter, you don't need that. We usually go on mesic soil types, and sometimes we can use moist soil types. We try to avoid dry sites and more kind of wet sites. Usually what's most common in Sweden is sandy silty moraine, and that's the perfect soil texture for fertilization. It contains usually water. Does not dries out, and still it's not too wet either. Sometimes you should avoid clay soils, of course, but sandy silty moraine is just fine. Mineral soils, we have usually podosols in Sweden. That's great, but we try to avoid peatland because, well, it depends on kind of peatland we have, but the growth response is somewhat different, and usually other nutrients is limiting on peatland, like potassium and phosphorus. We also kind of recommend conifers because our experience is largely from conifers. We have indications that when we fertilize deciduous trees, we have less response from deciduous trees. Usually have a strong response in the beginning, and then it fades away afterwards. But conifers, we have a lot of several hundred triads with conifers. And we try to avoid the most fertile sites because sometimes they are just so fertile that we will have no response on nitrogen. Usually you find them in southern Sweden and especially in southwestern Sweden. And we try to avoid shallow soils. I mean, you should have a quite thick soil layer because kind of for the rooting system and so. So that's also an experience that we should go not for shallow soils. And we don't, of course, fertilize stands that are severely damaged by insects or root rot or something like that. It was kind of a truth that the fertilization's response, if you have repeated fertilization, decreases for every fertilization. And there kind of was different ideas that the soil was saturated with nutrients or the mycorrhiza was kind of reduced because of the fertilization. And we tried to see if this was true, and we investigated a large series of fertilization experiments that have been conducted since the 60s and been going on for 30 years. And it was a kind of a fertilization and thinning experiment. So it was a lot of different combination of fertilization and thinning. But we found that this was not actually the truth. What we found instead is that if this was mainly the investigation in pine, but if the stands were unthinned, repeated fertilization instead increase the growth response for every fertilization. So it's kind of opposite what we thought before. So it was like 30% higher actually for unthinned stand compared to thin stands. And the main reason for that, well, we can't tell for sure, but what we think is that sometimes if you thin out a Scots pine stand too much, if you're going to fertilize and you will increase the foliage, you have less stems to increase the foliage, and maybe kind of the fertilization response can't be maximum then, and it will maybe only be 60 to 70% if you thin out the stem too much. But this is only a hypothesis. It could be one explanation, of course. And it's also quite interesting that the growth effect was not on the biggest stems and was not on smaller stems. It was the co-dominant trees that we found the growth effect. 80% on the growth effect was on co-dominant trees. Yes, I mainly talked about the fertilization during the second half of the rotation period, but I will shift to some extent to talk about fertilization in young stands, and it's quite different response. And another thing is that this is not practiced in Sweden at all, maybe on a very small scale, but it's only based on 12 experiments. We have not run more than 12 experiments with this kind of fertilization. So I had less information about it, but I will show some results about it. This is a trial that started in mid-60s in Sweden, and you see there the different bars, and on the x-axis this is stand age, and the y-axis is standing stem volume. And you have the reference, the red bars, and then you have different production development. What you call the G24 is that it will be 24 meters tall at 100 years, and the higher number, the higher productivity. So then you have also this G32 and G36. G36 is almost the highest production you can get in Sweden. You can have maybe a little bit higher than that in southern part of Sweden, the most southern part. Then you have different fertilization treatments, like nitrogen N2 means that you have 120 kilos of nitrogen every year in young stands of Norway spruce. Then you have a combination of nitrogen, phosphorus, potassium, and calcium. And you can see there that these development of growth is quite drastic. That within 25 years of treatment, you have a kind of a standing volume of almost 650 cubic meter for the best treatment there. And it's kind of have passed the best kind of production capacity you have in Sweden by this. And actually, I mean, if you have 650 cubic meter, you can almost clear cut the stand like that at the age of 45 years. And this is in central Sweden. So is this possible to kind of be transferred from an experiment to a more practical experiment that can be used in operational forestry? Well, the economy is not good if you're going to fertilize 120 kilos of nitrogen every year. It's too kind of intensive and it will not pay off, not a chance. But maybe you can kind of adapt this to a more practical scale. So they started kind of 20 years later another experiments, one in Flakalinen. It's 64 degrees north, so it's quite high latitude, and you can see the red bars is unfertilized while the solid green one is fertilized. And then you have this dash, this the kind of extra growth compared with the control treatment. So what you can see there is the extra growth is at least 10 cubic meter extra per hectare and year during this 20-year period. So, I mean, you see the different time periods, you have like 200 or 300% extra growth. And this is also in Norway spruce and in young stands. So it could be, I mean, this was the second experiment, and you have a kind of a sister experiment is down south, and it showed also drastic increase in production. What I can say about this ASA experiment in Småland, it's 57 degrees north, is that water can be a limiting factor because you have an irrigation experiment and irrigation combined with fertilization. But if you have a very dry year, you can have a kind of a reduction if you don't supply water. While in Flakalinen, this northern, more northern part, on 64 degrees latitude, you had no effect of water even if you fertilize very kind of intensely. So no effect of water in northern Sweden, but you have that in southern Sweden, and usually it occurs when you have very dry years. But we tried to start more practical experiments in 2001, and we tried to have different fertilization intervals, because fertilization every year, yes, that's quite intensive, but if you can fertilize every second year or every third year, and you have almost the same growth response, it will be much better economically. What I can say, that practical application of this kind of fertilization in young stands is that you start at like 2 to 5 meters height, and then you fertilize every second year 6 times, and then you might fertilize after that every fifth year, and You might do that 2 times and then it's time for clear cut. So usually in this, if you fertilize 6 times with every second year, you will close the canopy, and when the canopy closes, you can have a kind of a more distance between the fertilization intervals. That's our kind of recommendation today, but of course this could be changed and improved. But what these fertilization experiments showed is that it seems that in the beginning the fertilization interval matters, but after a while the fertilization interval have minor effects. So if you start every second year, and maybe you can go and fertilize every third year after a while. So it's quite promising. It will improve the economy quite much. Usually you have to fertilize a little bit more when you fertilize every second year and every third year. But you can see the red is the control and the green is fertilization every year, and then the gray bar is every second year and the white bars is every third year. And then we have even more practical experiments where you actually spread the fertilizer by a helicopter and you have kind of areas where you measured the growth in fertilized areas, and then you have kind of areas where you have not fertilized in the same stand, and you have quite large areas where you conducted these measurements. So Toftaholm, for example, it's in southern part of Sweden. Most of them is in southern part of Sweden. Gullspång is the kind of the third from the left-hand side. It's in central Sweden, and Hällefors in this kind of not the northern part of Sweden, but it's kind of northern part of Sweden. However, all these experiments show a quite drastic growth response. So it can kind of, you will not lose so much production when you go from basic research experiments to more practical experiments. So now actually there's a few companies in Sweden that are trying to scale this up in a practical scale. So we'll see what happens in the future if fertilization in young stands of Norway spruce can be something that will be practiced in operational forestry. We'll see. But this is conducted for example, in southeastern US, and I've been done that, and it's the kind of the same, what you call that, basis as we do here in Sweden, because they took, if you say so, and even the eucalyptus plantations in Brazil, they took this kind of fertilization, this nutrient optimization ideas and make it practical within kind of 5 to 10 years. But in Sweden we are kind of slow in many ways, and it takes instead it takes 40, 50 years in Sweden, and it takes only 5 years in other countries. So it's quite funny. On the left hand side you have actual growth. You see that in northern part of Sweden you can kind of achieve like 2 to 5 cubic meter per hectare year as an average throughout the rotation period. And then you move south and you see these green areas. The more greener, the higher production. But the kind of mean and average production throughout the rotation period is like 6 to 7 in southern part of Sweden. But of course, if you start a Norway spruce or a Scots pine plantation today, you will have higher production than this. You can easily achieve like 12 to 13 cubic meter. But if you fertilize, this is kind of a quick and dirty science that we use our experiments here. But what could we achieve in practical operational forestry, that you can increase actual production by maybe, let's be modest, but you can double the production at least per area basis by this kind of treatment. So all experiments are shown like 10 cubic meters extra per hectare a year as an average. Some information about other nutrients besides nitrogen. We have not so many kind of indications that have shown that other nutrients could affect growth, but this is one indication, not statistically proven, but you see there's these blue bars, this dark blue bar that are to the left-hand side of this group of bars. This is the control, and then you have an orange bar, that's the kind of irrigated and fertilized solid fertilizer. You see that's a significant difference between control and fertilization though. But then you see this dark red, it's a brownish bar. That's the fertilization without nitrogen, but you have all the other nutrients. So there was no kind of significant increase in the beginning, but after a while it had at least like 3 or 4 cubic meter extra per hectare a year. It was nearly significant, but it was not really significant. So there's a tendency that especially phosphorus could be limiting the growth, and this can be quite different from different parts of Sweden. But if phosphorus should increase the growth, it's usually in southwestern part of Sweden. It will not likely happen in northern part of Sweden. I think also that other nutrients are more important in young stands, and especially in Norway spruce, compared to old stands and Scots pine. This is quite new. This data is actually from 2 years ago. You see the red bar is unfertilized and the green bar is phosphorus fertilization. It had been supplied twice, 200 kilos of phosphorus twice, so it's 400 kilos altogether. But you see that it's a growth response of, well, a little bit more than 20 cubic meter per hectare, and it's still growing better. So it will be maybe it stays at 30 cubic meter extra. So phosphorus could increase, only phosphorus could increase the growth actually. So that's quite new for Sweden. It's not been proven statistically, but this is statistically different. But if you're going to have a growth response of phosphorus and other nutrients, you will have to go on to peatland. This has also been conducted in Sweden and also in Finland, quite a lot of experiments. And just a summary of these experiments is that they could increase production by 20 to 50% actually. That's wood ash, and wood ash contains no nitrogen, but it contains all other nutrients, especially potassium and calcium. And usually on peatland, it's phosphorus and potassium is the most limiting nutrients. So if you use them, you can increase the stem volume growth. Usually you can say also that if you have rich peatland, that you have a little bit more nitrogen, you have a greater response of phosphorus and potassium. And sometimes if you combine phosphorus and potassium with nitrogen, nitrogen can give you some extra volume growth. But I mean, it's if you're going to use wood ash would be most effective on peatland. But this environmental issues when you're going to do anything on peatland in Sweden. So wood ash and peatland is not kind of a thing that is operational today, little to some extent, but not much. And you see here is a quite extreme case. It's in Finland. It's an experiment in Finland where you supplied 8 tons of ash and 16 tons of ash. And that's an enormous amount of ash. Usually in Sweden, if you supply ash, it's like 3 tons. And so, but you see here, if you have no phosphorus or or we have no ash, there's no extra production in at all. It's, you see, it's a flat line there, it's an almost flat line along the x-axis. It's only 25 cubic meters growth for 50 years. But then you see that when you supply wood ash, it's quite drastic. You have a normal stand almost like 400 cubic meter. So, but that's extreme. You can't expect that usually. Okay. Now it's kind of stopped. See if I can do like. Okay. Let's see here. Yes. Now I will swap a little bit. I will not talk about fertilization. It's more like what this means in terms of carbon storage or carbon uptake. So this is how we calculate. This is quite quick and dirty calculations. It's not usually how scientists do, but it's a way that could be useful anyway. So in Sweden, we said that when you're going to convert 1 cubic of stem wood to total biomass, you have to multiply with 1.75. Then you include also branches, coarse roots, and needles or foliage. So it means that it will become 1.75, and then you use the basic wood density as an average across Sweden, and for Scots pine and Norway spruce, it's 0.42. It's 420 kilos per ton per cubic meter, or 0.42 tons per cubic meter, and then you will have 0.75 ton dry weight per cubic stem wood. I hope you follow my calculations there. And then if you're going to convert this dry weight to carbon, it's quite easy, because 50% of the dry weight is carbon. So then you multiply this 0.75 by 0.5, and then you will get a number there. And then if you're going to convert carbon to carbon dioxide, because you take up carbon dioxide and then you will build in the carbon. So if you're going to calculate actually the carbon uptake, you have to use the molecular weight of carbon dioxide and divide it by the molecular weight by carbon. And it's like the molecular weight for carbon dioxide is 44, and for carbon is 12, so that means a ratio of 3.6. So in the bottom here is the whole calculation. So it means that 1 cubic meter of stem wood is equal to almost 1.4 ton of CO2 uptake. I hope you followed this, but this is approximately like 1 cubic meter is equal to 1.4 ton uptake of CO2. And then you can calculate if your stand is growing 10 cubic meter per hectare a year, and you have to multiply 1.4 ton by 10. This could be done for more specifically for different tree species and so. Yes, this is quick and dirty calculations. If let's say that fertilization, it gives 10 to 20 extra cubic meter of stem wood per hectare, it means that you use this 1.375. It means that the range is like 14 to 28 tons CO2 per hectare. But then you have to also consider that the fertilizer creates emissions, for example, of CO2, but also of nitrous oxide, laughing gas that are quite potent greenhouse gas. But if you look at how much 150 kilo nitrogen emits and the transport and the spreading in the forest, it's equal to 735 kilos per hectare, or 0.7 tons per hectare. So the net budget, you have to subtract that, and it means that the plus, it's like 13 to 27 tons CO2 per hectare if you kind of subtract the emissions of CO2 and nitrous oxide when you produce the fertilizer. So, for example, if you fertilize 10,000 hectares, it's equal to 0.13 to 0.27 million tons CO2 per year. So that's quite a lot. I don't know the emissions of kind of your city or your kind of region, but you can do a lot of CO2 uptake by fertilizing. I just want to show the kind of the difference. If you fertilize in older stands, you usually increase the kind of the CO2 uptake. This graph is that this green area is CO2 uptake, and the red area is CO2 emissions or release. So in the generation phase and in young stands, you usually emit CO2, and then during the rest of the rotation period, you have a large uptake of CO2 until you clear cut again. So if you fertilize, you will have see this arrow goes up. But if you fertilize in young stands, you will also move this area where you have a positive uptake of CO2 as well. So that is kind of two ways to increase the amount of CO2. So I want to show you just some effect of fertilizing in young stands as well. But increased growth in general, we say that it could have a different kind of effect. It increased the storage in the forest, of course, but it could also increase storage in different products. You build in, for example, wooden houses and have panels and so, and it lasts for a long time. And so there's also increasing stock in buildings and so. But then you can also have increased substitution because if you increase the growth. And just a shorter explanation what I mean with substitution. For example, in Sweden, we sometimes take out forest residues and use them for fuel, for heat, for power plants. And let's say that you leave the forest residues in the forest, you don't collect them, then you will have they will decompose, and most of the carbon will emit as CO2. So after 20 years, maybe 70% of the CO2 is released because they decompose. And then you still have emissions of oil. So you can say that in this case you have two emissions. But if you use forest residues and use it for energy, you might reduce the use of fossil energy, and then you have only one kind of only emissions from the residues. So you can say you replace fossil fuel. Another way to substitute is, example, if you replace concrete in buildings, because there's two ways that the energy that you use when you create concrete consumes a lot of energy, and it depends, of course, what kind of energy source you have. But if it's a fossil energy source, you have to use fossil fuel, and then at the process you will emit CO2 in the process. So what we usually says is that to some extent this is also quick and dirty, but if you use 1 cubic meter of wood and replace coal, it means a substitution effect of 700 kilos of CO2. And it's less for oil because oil is a little bit more effective as an energy source compared to coal. So the substitution effect is a little bit less. It's only 500 kilos of CO2 for 1 cubic meter of wood, and fossil gas has the lowest substitution effect. But this can actually be compared with that 1 cubic meter of storage in the forest could mean 1.4 tons. So it's, well, we can should we use or should we store? I think we should do both. Okay, I see I miss a picture. Actually, I had another picture. But if you replace concrete, you can have a substitution effect of 1,000 kilos to 1,500 kilos. So that's much more than if you replace fossil coal or fossil oil, for example. But this is more kind of research-based calculation that we're using a life cycle analysis, and you compare fertilization in young Norway spruce stands with control stands. And we have also used 10% of the forest land will be fertilized in this way. It's quite a lot, of course. It's like 2 million hectares, more or less. And then you look at the storage in trees throughout the rotation period, but also what happens in the soil. If you have a higher production, we'll have a higher litter fall, and we'll have actually more carbon in the soil if you fertilize. And then you also calculate the substitution effect. So the solid bars is fertilized, and the dashed lines is unfertilized. So what the difference is, like if you use this on 10% of Swedish forest, on Swedish forest land, means 2 to 14 megatons CO2 per year, and the total emissions in Sweden is like 55 tons per year, and it means like maybe 25 to 30% of our total emissions in Sweden. That's what I intended to say. So thank you for listening.